Hey everyone, and welcome back to the Deep Dive. You guys have sent us some really cool research lately, and today we're going to be diving into neuromorphic computing. Seems like you're all ahead of the curve on this one.
It's definitely a hot topic.
Yeah.
We're going to unpack exactly what it is,
Yes.
why it matters, and some of the challenges researchers are facing.
So, for those of us who maybe haven't heard the term before, what exactly is neuromorphic computing? Is it like building a brain in a computer?
It's not about recreating a human brain exactly, but more like taking inspiration from how efficient it is. Imagine a system that processes information as fast as your brain, but uses way, way less energy. That's kind of the big idea here.
Okay, so less about like consciousness uploading, more about like borrowing the brain's best design tricks.
Exactly. They use something called spiking neural networks, and it's different. So instead of data flowing continuously, it's sent in pulses or spikes, kind of like how real neurons talk to each other.
Spikes. So there's like a tiny rave happening in our computers. Okay, but seriously, what's the advantage of using these spikes?
Efficiency. Really, that's it. Imagine a system that only uses power when it needs to, like otherwise it's just chilling out, not using any energy.
Oh, like those motion sensing lights, the ones that only turn on when you walk by.
Perfect example.
I love those.
It makes neuromorphic systems incredibly power efficient, which is a big deal for everything from your phone to those massive data centers, the ones that power like the internet and everything.
Right, right. So we're talking about some serious real-world impact then. The research mentions some pretty complex stuff. What kind of problems can neuromorphic computing help us solve?
Oh, it's a huge range, and it's growing all the time. Like, think about optimizing really complicated systems, like finding the absolute best route for deliveries, or even solving like seriously complex math problems.
Whoa, okay, from deliveries to like advanced math equations,
Yeah.
that's quite the leap. How does it work for something as complicated as, say, optimization?
Okay, so imagine you're trying to figure out the most efficient way to, I don't know, schedule a fleet of delivery trucks, right?
Hmm.
A normal system would have to analyze every single option one by one. But a neuromorphic system, it uses this cool thing called a random walk, where it can explore like tons of possibilities all at the same time, and then boom, finds a good solution way, way faster.
Okay, so it's like those robot vacuums, but instead of cleaning, they're finding the fastest routes, and they can like adjust to traffic and stuff in real time.
Exactly. Because of how they're built, they're great at handling new data and making decisions super quickly.
Okay, so it's like if a traffic jam pops up, no problem. The neuromorphic system is already rerouting those delivery trucks.
Right.
No more waiting for like a slow computer to catch up.
Exactly. It's like problem solving on the fly, and it's what makes this tech so exciting.
Yeah, it sounds amazing, but I imagine there are like some speed bumps along the way.
Right. Of course, it's still early days.
Right.
One of the biggest challenges is how these systems are actually built. So inside you have all these artificial neurons, but the actual physical parts, they're not always exactly the same. It's like tiny inconsistencies in each one.
So it's like you're trying to build a perfect machine, but all the parts are a little bit off, like my brain trying to assemble furniture. That sounds like a nightmare for, the engineers who actually have to make this stuff work.
It's a huge challenge, and researchers are working on ways to like either make the parts more consistent or build systems that can just like work around those inconsistencies.
So basically teaching computers to deal with imperfection, just like we do every day.
Exactly.
Now, the research also mentioned this thing called spike vanishing. Sounds kind of ominous. What's that all about?
So basically, as information travels through the network, it can sort of fade out. Like the signal loses strength and it makes it harder to process.
So it's like the further the information has to go, the quieter the signal gets.
Yeah.
Until eventually it's like too quiet to hear.
Yeah, something like that. And figuring out how to amplify those signals is a big focus for researchers.
Wow, it's amazing how complex this all is. Now, speaking of complex systems, I have to ask, how is this different from those like neural networks I hear about all the time with, AI and machine learning? It kind of sounds like the same thing.
That's a really good question, and it trips people up all the time. It all comes down to time. Traditional neural networks, they process information in these distinct steps, like looking at a bunch of photos one after the other. But neuromorphic systems, they're dealing with continuous streams of information, more like watching a video.
Traditional neural networks are like reading a book, and neuromorphic computing is like having a conversation. One is static, and the other one is like constantly changing and evolving.
You got it. And that ability to process information in real time is what makes neuromorphic computing so powerful, especially for things that need to adapt constantly, like robotics or, anything that deals with a lot of real-time data.
Okay, yeah, I'm starting to see why everyone is so excited about this. It's like a whole new world of computing is about to open up.
Exactly. It has the potential to change, well, almost everything. And it's not just theory.
Yeah.
People are actually building this stuff.
Okay, yeah, the research mentioned some real-world projects, like actual implementations of this technology.
Yeah.
What stood out to you?
Well, one of the most exciting things out there is this chip that Intel developed. It's called Loihi.
Loihi, okay.
Yeah, it's specifically designed for neuromorphic computing.
So what makes it different from like a normal computer chip?
So normal chips, they follow a clock, right?
Right.
Everything happens in a very strict rhythm.
Right.
But Loihi, it processes events as they happen. It's
Okay.
more like event-driven, like we were talking about earlier.
Oh, okay. So instead of waiting for like a clock to tell it what to do, it's reacting to like whatever's happening in real time.
Exactly, which makes it crazy efficient for things that are unpredictable, like, anything that involves interacting with the real world, sensors and stuff like that.
That's cool. So Intel is working on this. Is anyone else like trying to build these neuromorphic chips?
Oh, yeah, definitely. IBM has this other chip. It's called True North.
True North. Okay.
Yeah, and it's a completely different beast.
Oh, yeah. How so?
Okay, so if Loihi is like a small island, with a few specialized things on it, True North is like a whole continent.
Okay.
It has millions of these artificial neurons all connected together.
Whoa, that's like way more complex than Louis.
Oh, way more complex. But it also means it can handle like seriously intense problems. Things like pattern recognition, learning, making decisions in real time, all that
So
stuff.
it's like it's getting closer to how our brains actually work with all this fiction.
It's taking inspiration from nature.
That's so cool. Okay, so we have these chips, but how do you actually like program them? Like what's the software side of this look like?
Yeah, it's definitely its own thing. You can't just like boot up Microsoft Word on these chips.
Right, right.
Uh,
So there are specific tools for this.
yeah, there are some really cool frameworks out there. So one that a lot of people use is called Nengo,
Mango. Okay.
and it uses Python, which is nice.
Oh, okay, that's a good sign. Isn't Python supposed to be like a little bit easier to learn?
Yeah, it's a good starting point. And then there's another one called BindsNet, and that's built on top of PyTorch. So it's for people who are already working with like deep learning stuff and want to dip their toes into spiking neural networks.
So it's like, it's like having the right tool for the job.
Exactly.
Okay, that makes sense.
Yeah.
But even with these tools, it still seems like a pretty challenging field, right?
Oh, absolutely. I mean, we've talked about the hardware challenges, but even just figuring out how to like design algorithms for these systems is a whole other thing.
Because it's such a different way of thinking about computing, right?
Totally. It's not just about, translating old ideas to new hardware. It's about coming up with completely new approaches that like really leverage the strengths of these neuromorphic chips.
It's like you can't just like translate Shakespeare directly into, I don't know, Japanese or something. It's a whole different way of thinking about language, right?
Exactly.
You need like a whole new approach.
Wow.
This is fascinating. So we've talked about like the nuts and bolts of how this all works, but what's the like big picture here? Why should we even care about neuromorphic computing? What's so revolutionary about it?
Well, it's not just about building, faster computers. It's about changing the whole way we think about computing, like fundamentally.
Okay, I'm intrigued. Tell me more.
So for decades, computers have worked by keeping processing and memory separate, right?
Right.
And it works, but it creates this bottleneck. Like imagine having all the ingredients for a gourmet meal, but they're like scattered all over the kitchen.
Okay, yeah, you could still make the meal, but you'd be doing a lot of running around.
Exactly. And your brain, it doesn't work like that. It's got processing and memory all jumbled up together, which makes it super efficient. And that's what neuromorphic computing is trying to do. It's like instead of building a faster horse, we're inventing the car.
Okay, I like that analogy. So what kind of like world-changing applications are we talking about here? What could this like actually enable?
Oh man, it's huge. Like imagine AI that can actually learn and adapt in real time, like as fast as a person, or, data centers that use a fraction of the energy they do now, or even like entirely new types of sensors that can understand the world, like way more like our senses do.
It sounds like we're talking about a paradigm shift in computing. This is getting kind of philosophical now,
Yeah.
but with all this talk of like brains and computers and stuff, are we on the verge of like creating truly intelligent machines?
Yeah, that's the million-dollar question, isn't it? I mean, we're definitely building systems that can do some pretty amazing things. Things that, might have seemed like intelligence a few years ago. But whether that's actually intelligence or just like really good mimicry, that's a whole other can of worms.
Right, yeah, like just because something walks like a duck and quacks like a duck doesn't mean it's actually a duck, right?
Exactly. For now, I think we're still in the like mimicry phase. We're learning how to copy certain things the brain does, but actually replicating its like full complexity. That's a long way off.
Okay, so as we wrap up this deep dive, what's the like one big takeaway you want to leave our listeners with? What should they be thinking about as this technology keeps, advancing?
I think the biggest thing is don't underestimate how fast this field is moving. What seems like, crazy sci-fi today could be commonplace in a few years.
Yeah, things are definitely accelerating.
And the other thing is, engage with this stuff. It's not just about the tech, it's about what it means for us as humans. Like, what is intelligence? What are the ethics of building machines that might be smarter than us? These are questions we all need to be thinking about.
Absolutely. It's a conversation that everyone needs to be a part of.
Hmm.
Well, this has been a wild ride. Thanks so much for like walking us through all of this.
Happy to do it. This stuff is fascinating.
And to you, our listener, thank you for sending us this awesome research that sparked this whole conversation. Keep those brains buzzing, and we'll see you on the next deep dive.